a theory which describe this physics. So we need to clearly understand the big difference from the previous slide, which is how to understand not just emergent space, but emergent space and time as well. Now this is something that people in this business have appreciated for at least a decade. If you go to, conferences, the grand poobahs on the subject will give summary talks where they'll say, we have to understand emergent time, we've got to understand emergent time. It's very important to know what the crucial questions are, but this is a hard problem to just get up in the morning and work on. Okay? You can't just get up and go to your office and say, today I will work on emergent time. Okay? That's, and part of the reason is that it's clearly going to require some massive conceptual leap. Because, again, what the heck does it even mean? How do we even, what should it mean? So, are we just screwed? I mean, you might think we're just screwed. That's a totally reasonable attitude. This is just too hard a problem. We should work on other problems, which are not as hard, maybe, or just other things. Because also, it's unlikely we're going to get much direct feedback from experiments for this kind of question. So maybe we should just give up for like a few hundred years until someone comes along. Maybe some Newton prime comes along with the appropriate kind of brain to make progress on it. So, but a little bit further thought leads to a more encouraging strategy. We can go back and think whether this has ever happened to us before in physics, where some clearly hardwired cherished notion was lost in the more correct theory, and of course it has. Most dramatically in quantum mechanics, right? We went from having a theory where determinism was hardwired to a theory which was not deterministic. So let's just go back and see how we might have, how this leap could be explained to a classical physicist. Let's do a thought experiment. Imagine that there's a ghost of nearest future that visits a classical physicist in the year 1780, okay? And wakes him up and says, in 1930, determinism is gone. And then they take off into the night. Okay, so well, this classical physicist is clearly going to have a hard time sleeping. He's wondering, what could that possibly mean? Determinism is gone, but how could it be? I mean, it's hardwired into Newton's laws. But they're very excited. Clearly, they have to write a paper soon. Otherwise the ghost of nearest future will visit some other theorist and they'll write a paper, so they got to do something about this. So what should they do? Well, there's a good and a bad thing that you can do with this information. The bad thing to do is try to guess the right answer. Say, okay, determinism is gone, so I should modify Newton's laws in such a way that it's not deterministic. Maybe I'll add some stochastic terms to it, so it's not deterministic. You could do that, but it's massively unlikely that you're going to get the right answer that way. In fact, you probably won't. Right? The right answer, which is quantum mechanics, is so far away, just in its formulation and the we've got to think about Hilbert spaces and wave functions, and how the heck are we going to get there starting from Newton's laws? It's just impossible to make such a gigantic leap. But there's a more conservative, but much more reasonable and effective strategy that you can take, which would be, well, this is very distributive. There isn't any determinism. That must mean that the determinism that's hardwired into the physics that, let's forget about guessing the right answer. Let's just think about the physics that we have right now. It must be that that determinism isn't fundamental to what talking about this physics. Even though that's where it came from, thank you Newton, there must be some other way of talking about even the physics we have right now that doesn't make such crucial use of this notion of determinism, because it actually really isn't there, fundamentally. The correct theory doesn't have it. So that means there must be some way of talking about all of physics, not just the correct theory, but all of physics, in a way that doesn't have that idea. Okay? So that's a much more fruitful strategy, because you now start trying to cast about and see if it's possible to reformulate the physics you have right now, Newton's laws, in a way that doesn't make determinism so manifest. Okay? And if you succeed, you've sort of gotten 90% of the way there, because you've managed to figure out how it is that something can look deterministic and actually be deterministic without having determinism as a fundamental notion. Now, does such a formulation of classical physics exist? Oh, so I'm going to jump ahead for this. Sorry, I put it in the wrong spot, maybe. It does. It's the principle of least action. The principle of least action is a way of talking about classical physics or determinism as it manifests. When we first learned about it, it's pretty startling. Does particle A think about all the ways it can go to B and decide which way it's going to go to minimize the action? It doesn't look like it's going to be deterministic. It turns out to be deterministic sort of accidentally, as a consequence of the rules for how you do the variations and the kind of paths you allow and so on. But this is something which, when you discover it, is like, aha, so there is a way of talking about classical physics where determinism isn't manifest. Why does that formulation exist, in fact? Even if there was no ghost of theorist future, this is actually the way things really happen without, I guess, maybe that's how Lagrange and Laplace got it, God knows, right? But they actually ran into this formulation. They were really confused. They really thought it was very strange that there was this totally different psychological starting point for classical physics. But we now know why it exists. It exists because the world isn't classical, it's quantum mechanical. And the h-bar goes to zero limit of quantum mechanics isn't to Newton's laws. The h-bar goes to zero limit of quantum mechanics is the principle of least action. So this is a strategy. When we know there's a principle we have to lose, in this case it's something as dramatic as space-time and time itself, and I didn't emphasize it, but it's not just space-time. It may even be quantum mechanics and unitary. Precisely because of these very subtle cosmological problems that I alluded to, we don't even have precise quantum observables. So it's the first time that it's the first time we've ever encountered a deficiency even in the structure of quantum mechanics to allow us to address certain kinds of questions. So both locality and unitarity, both space-time and quantum mechanics might be on the chopping block. But the way to make progress isn't to just wildly guess at the right answer. A way of making progress is to try to take the physics that we know is local and is unitary, satisfies all the usual rules, standard physics that we have, and try to rewrite it in a way that doesn't make such heavy use of those notions. Okay? So that's the highfalutin motivation. Now, there's a second set of much more concrete motivations. So let's descend now back to Earth, and actually outside Geneva, and talk about something else. So the LHC is up and running. It's a spectacular machine. There's something that many kinds of new physics that many of us hope will be discovered at this accelerator. Things like the production of supersymmetry and other particles like this. This is indeed speculative. Okay? But just so you have an idea, the rate at which this kind of new physics would happen, if it's there, if we're lucky, it would happen once a minute or so. We'll produce these superparticles once a minute or so. And the superparticles don't come out wearing a name tag saying I'm a superpartner. They very rapidly decay to ordinary particles. Okay? So a typical process is two gluons inside the proton come in, they collide, two superpartners of the gluons come out, but they rapidly disintegrate to themselves to two gluons and some other stuff. But what you see is two gluons going in and four gluons coming out. And this is what you have to see and dig out. It happens about once a minute, hopefully, if we're lucky. The problem is that much more boring, ordinary processes make two gluons come in and four gluons come out much more rapidly. The ordinary strong interactions have the gluons interact with each other, and so this happens. Okay? And it happens hundreds of thousands of times a second, not once a minute. So you have to learn to understand and control that and beat down these huge backgrounds to pick this needle out of the haystack and discover these superparticles. So for this reason, theorists in the late 1980s had to start to learn how to actually calculate these processes. And there are processes that sound a little complicated. Two gluons goes to three gluons, two gluons to two to three, two to four. Okay? And you have to go to these pretty high final states just because they had to, not because they're masochistic, but they really had to for practical, totally practical reasons. Okay? As grungy, responsible reasons that you could possibly find. Now, in principle, the standard formalism of putting together quantum mechanics and relativity, quantum field theory, tells us some rules for how to calculate these processes. This is, after all, what made Feynman famous. What made Feynman famous wasn't that he invented something new. He just took the laws of relativity and quantum mechanics and put them together, but he figured out how to do the calculations in a way that made locality in space-time and quantum mechanical unitarity manifest at all the steps in the calculation. That's the point. Made locality and unitarity manifest, and that's what the Feynman diagrams do by giving you a space-time story for how the particles are interacting with each other. Okay? So you open up your textbook, and you try to start calculating this process. You're a grad student in a field theory course, so you open up your favorite textbook, you copy out the Feynman rules, you start doing this calculation. Feynman got famous for calculating 2 to 2 processes. They're the ones that you most often care about, like confidence scatters. But here we need, for practical reasons, 2 to 3, 2 to 4, so we start doing the calculation, and something horrible happens right away as you go beyond 2 to 2. Even at 2 to 3, something terrible happens. I've gone 2 to 4 here. Even in the lowest order of approximation, there are 220 Feynman decimals. And I've written 10, it's actually hundreds of thousands of terms when you actually expand it out. Let me show you what the answer looks like for 2 to 3. Okay? It looks like that plus 24 more pages like that. That's just what happens if you open up the textbook and you copy it out. There's a reason why no one who's taken the filter course has been assigned the 2 to 3 equal ones. 2 to 2 is manageable. You can do it on half a page. 2 to 3 all of a sudden explodes to 25 pages. 2 to 4 is 80 pages. There's something very wrong. Well, actually, you might not think there's something very wrong. You might think it's just tough. It's life. It's complicated because it's complicated. In fact, why is it complicated? Well, it's just dummy. 2 things are coming in. This can bang into that, the thing into that, the thing into that, and all this crap can happen, and 4 things go out. So, of course it's complicated. There's zillions of ways it could happen, and just tough. That's just life. It is complicated. Looks complicated because it is complicated. And if that was the end of it, that would be that. That's in fact what you naively think. Because giving this space-time interpretation sure leads you to suspect that it is complicated, intuitively, calculationally, in every way. But these poor people, you know, the experimentalists kept bugging them, can you please compute this back time? Can you please compute this back time? Okay, it's complicated, someone's got to do it. You know, it's not the exciting thing, but I'll sit down, I'll do the hard work. I have to invent a lot of tricks. So these people in the late 80s had to invent lots and lots of tricks. And 2 people, theorists at Fermilab, Park and Taylor, developed lots of these tricks. They wrote a series of papers